Welcome to the course on two-dimensional signal processing, principles and practices. As we have done the various transforms like DFT, DCT, DST and Hadamard transform, we will be doing KL transform as well, which is different from all these things in a way, so that we would get into it. Also, in this few lectures, this lecture and the next lecture, we'll do the implementation of the transforms what we had done and how do we get this basis signals or basis images for 2D signals. Also, how to reconstruct them from knowing the basis images or basis signals. So first we'll take this the DCT pair, as we know that 1D DCT pair for the given sequence x of n. So the basis function is given cos by k by 2n into 2n plus 1. So this is for the case of obtaining the DCT coefficients. We have taken some examples and how the coefficients are specifically on the low energy, low frequency regions, and how this energy compaction property of the DCT was. So these things we had learnt in the previous lectures. Now, if you're taking this DCT pair, that from the DCT coefficient, you can get the signal back at itself. This is an invertible one. So the inverse transform exists for DCT this thing. So once we know the coefficients, we can get back the signal. For the given signal, we can get the coefficients as well. So for this case, that the basis function, if we take cos pi k 2n into 2n plus 1, so for wk is the constant, which is for k equal to 0 half, and then it is 1 for remaining k values, that is 1, k is varying from 1 to n minus 1. So using this, how do we get this basis function using the codes? So we have taken the length of the n is equal to number of points to plot the basis function as 51, and that is varying from 0 to 50, the n which is mentioned in the equation. Also generate a figure which is for the k is varying from 0 to 7. So the bin indices here, this is the same meaning of DFT bin indices, where k varying from 0 to n minus 1. So this we have taken a 0 to 7, so to generate the basis function. So 0, 1, 2, 3, 4, 5, 6, 7 and different bin indices indicates the different meaning in the DCT coefficient. So the subplot is used to generate these plots. Okay, so totally 8 plots here for 0 to 7. So this is given as 8 subplots and 8 rows and 1 column, where k is varying, the first plot, second plot and so on. So 8 plots will be generated here. So for this, basis function is taken cos pi k 2n plus 1 by 2n. So the DCT basis function, so just it is given as x, it is not the input sequence, it is just a basis function to plot it. So with this x, and we will plot for the different k values, and that's for particular n varying from 0 to n minus 1. So where n is varying, and for different k values, first fix k equal to 0, and then a vary n, and to get this x value, plot this x with respect to these n, the n which is varying, and these are the properties of the plot. So we can just fix the limits of these x and y axes, and in this fashion, as you know that this is just giving the title. And as we plot this DCT basis function, which is here, so k equal to 0, which is giving the 1 value 1 for 0 to 50. In this plot, k equal to 1, this would give the half cycle of the cosine function, and whereas k equal to 2 gives the full cycle. So when you want to extract this fundamental from this, as we had, if you recall, this same thing they had mentioned in one of the lectures as well. So if k equal to 2, that gives the fundamental of it. K equal to 3 would give 1.5 cycles of it, and k equal to 4 will give the 2 cycles, that is second harmonic details. And k equal to 5 and k equal to 6 is giving the 3 cycles. That is that if you check between the 0 and 50, there are these basis functions complete the 3 cycles. So k equal to 7. So this is plotted up to 0 to 7. It can vary, depends on the number of harmonics we are interested in and the number of points you take it, and as we take the n varying, and it can be varied as well. So this is the DCT basis function. So why do we need this basis function? So using these bases, we are just when we are computing the DCT coefficients, we are correlating that x of n with this k values of this. If it is correlating, then this type of signal exists in x of n, this gives the coefficient, or the coefficient is high. Otherwise, the absence of coefficient can be observed in the correlation function. So this basis function helps in reconstruction as well. So if we know this basis function and there is a coefficient which is transformed, using that we can reconstruct it as well. So the case of 1D DFT pair for similar basis function, to get it, that analysis equation and the synthesis equation of DFT is known. 1D this is. So we are correlating with x of n cos 2 pi kn minus j 2 pi kn. So we are correlating the coefficient, correlating these two sequences to find out whether the similarity index or exist or not. So if such kind of the fundamental is exist, and then it gives you some value. We saw this details and studied through an example here, which is having the endpoint DFT. So the synthesis equation, if you know the coefficients, we can get back the sequence. This is also an inverse transform. So for this, how do we generate the basis function? So they're taking the same kind of number of number of points, and the 0 is varying 0 to n minus 1 variation of n. We get the figure. And for the k of 0 to 7, that is 8-point DFT we had taken. So if you recall, and then generating the subplots, and the real part is that e power minus j 2 pi k n by n, in which the real part is cos 2 pi k n by n. So now we get, and the imaginary part is minus sin 2 pi k n by n. So now these two, we will plot this real part separately and the imaginary part separately for the different k values, and where n is, this n is fixed as 51 and this n is varying from 0 to n minus 1. So these are the plot properties, and the axis limits we could also be, and the title. These things doesn't give much information in this code, but to make the plot properties on the code itself, it is helpful to plot it. So only DFT basis function which we got through the code is where k equal to 0, and that this would give 1, that blue one, and the red is giving the imaginary one, k equal to 0, it is giving 0. And then k equal to 1, again you can see the fundamental which is completing one cycle here with both cos and sine. Okay, and k equal to 2 is corresponding to the second harmonic, and the k equal to 3 is third harmonic, fourth harmonic, fifth harmonic, sixth and seventh harmonic. So we just check this harmonics with respect to the x of n, correlating it and finding the coefficient in the DFT coefficient. So this is for the 1D DFT basis function. So how do we generate this basis function, and what is the meaning of this basis function? How does it look like in for 1D sequences? And similarly we can extend this idea of taking it for the 2D signals, as we take an image, that image basis for images, how do we generate them for DFT as well as DCT and DST also, we'll see. Then the 2D DCT, if we take that definition, this equation is known to us, that x of n1 comma n2. So now the signal is two-dimensional. So the basis functions in both the directions, we have this cos pi 2n1 k1, 2n1 plus 1, as well as cos pi 2n2 k2, 2n2 plus 1. So where k1 and k2 are between 0 and n1 minus 1 and 0 and n2 minus 1. This is 0 otherwise. So this is to obtain the coefficients, DCT coefficients, and we have seen the energy compaction property of this as well. So now for the inverse DCT, what we had is, if knowing the coefficient, we get back this sequence x of n, that is 2D sequence here. Using this W1 and W2 of K1, K2 carries this one meaning of this. It is when K1 is 0, it is half, and K2 is 0, it is half, and other values of K1 and K2, these are 1. So this is the extension of this 1D DCT. And using this, now the basis function we would plot. The basis functions are can we take that for an n equal to 8, that is 8 by 8, like the JPEG, it is used generally, the 8 by 8 size. So it can be of any size also. We just to illustrate it here, the size block of 8 by 8 is used, and this DCT matrix of n, if you just use it as a MATLAB, then DCT MTX of n results in the DCT kernel. So you just recall the DFT kernel, where the DFT as a linear transformation we did in 1D, so where the total factor matrix we calculated. So this one would give you the same thing, like cost basis function from the cost basis function, that for n equal to 8, it would give the DCT kernel. So this DCT kernel, now we can take the column wise and the row wise as well. So u is varying from 1 to n, and v is varying from 1 to n. This is to just for the plotting we take this DCT MTX, or we can do this with the cos of pi by 2n1 k1 into 2n1 plus 1, and cos of pi by 2n2 k2 2n2 plus 1. So if we use those basis function and plot it as well, we can get the same plot. So here it's a built-in function. DCT matrix can be obtained directly from the MATLAB. So the basis images are generated like that. So C of this column u comma colon transpose, and C of v colon v comma colon. So if we multiply these two, it would give the outer product and give the each basis images, and we can use the subplot to plot these things here of n by n size, that is 8 by 8 here. So we would for image SC, that of B would create an image section in which you can different color maps can be used. Here it's used color map gray, where this can be of for different generating different images of intensity plots and so on. So this color map can vary. So here we used only the gray color map, which can give the better visualization of the basis images. So this is for axis of. These are some of the properties to generate the basis images. Let us see the DCT basis images, where you can see this K1. Actually, we can get this through this plot through the basis functions cos of pi k1 to n1 to n1 plus 1, or cos pi k2 to n2 to plus 1. So fix n1 and n2 as we have done, and the varying this k1 in this is varying of k1 from 0 to 7, and k2 in this direction from 0 to 7. So where k is this is 0, k1 0, k2 0. So this is the plot, and k1 1 and k2 0. So this is the plot, and you can see the stripes varying in one direction, k1 direction, only this vertical stripes you can see in this in the first row, and similar if you take the first column, that you can see the horizontal stripes, so which is referring to the k2, and this is referring to k1. So if you have both k1 1 and k1, this is 0 0 1 2 3 4 5 6 7. So similarly we can have it here. This is what we got it. So 1 and 1, this vertical stripe and horizontal stripe, you can see this diagonalism can be obtained here in this basis image. Similarly here, this is for k1 2, and here k2 2. Okay, so this when both are existing, k1 and k2 in this function, then this would give 1 2 3 4 and the center. So the pattern would vary, depends on the, here we can also see that horizontal and vertical 7 and 7 for here various k1 and k2 values. These are the basis images for the DCT. So if you know this basis images, and then we can from the obtained coefficient we can get the reconstructed signal as well. So this is to have an idea that how this basis images would look like compared to the 1D DCT, where the signals, the fundamental, here the image also contain the sinusoidal and cosinusoidal signals in both the directions. So it can be in the horizontal direction as well as vertical direction. It's a combination of sinusoidal and cosinusoidal signals in both directions, horizontal as well as vertical direction. That's the image consists of these things. Like the signal can be arbitrary signal, can be with a combination of the or the periodic sequences with the sum of the sines and cosines. So similarly the image also can be written in terms of sines and cosine in both the directions. So that's what we try to mean here. This k1 is the bin index which gives the fundamental second and third and whatever the harmonics you have, and the horizontal and vertical meaning of this and combination of this horizontal and vertical stripes in all these images so that the image pattern would vary, and the signal can be written in terms of this basis images. So for the DFT, similarly for the DFT pair, so what are the types of DCT and DFT images basis function? So the here 2D DFT pair is given. How do we obtain this given 2D sequence and take the 2D DFT? So here 1D DFT is extended, 2D DFT in the 2D DFT e power minus j 2 pi k1 n1 by n1, and here also e power these basis functions. We would now plot these two for a real and imaginary case. So the inverse DFT, so doing the coefficients, we can get back this sequence. But the thing is here j 2 pi k1 n1 n1, so you have, it contains the real and imaginary parts as well, whereas in the DCT it is only real part. Now getting into the DFT basis images, so what we can do is it can be of any size, n is 8, or so just to show this n is taken as 8. So you give the XY mesh grid, create this mesh grid for 0 to 7 just from this side and x and y directions, and this is upscaling for some smoothing, and the real part is here. You can say this color and white, it would create the plot. Then you have the plots you have is a tiled one. So to lay this out to the tiles, you can use this n by n tile spacing and padding of all the properties can be set, and we get this real part. You can see cos 2 pi, that is k is k1 and k2. U and v are used in this, v in the horizontal direction, u in the vertical direction. So is uv are the k1 and k2 we have used. Instead of that, this is k1, it can be used k1 and k2 as well. So the image section SC, which is giving the image plot in which it can be resized for some of the details, and this axis of and color map is this. So you can have the axis as -1 to +1 end. So now for the imaginary part, similarly, if we get into that imaginary part plotting, these two things we are going to see it as a separate tiled plots, so that u and v are varying. Similarly, instead of cos, we had taken minus sign, k1 and k2. So this is the t power j theta. So we had also plotted with the image section color map and give the thing. So this is the to the DFT basis image of a real one. That is, we can get the same with the plotting cos 2 pi k1 n1 by n1, cos 2 pi k2 n2 by n2, for k1 varying from 0 to 7 and k2 varying from 0 to 7. So this is the plot for 0, 1, 2, 3 and 4, 5, 6, 7. So similarly, this side varying. So you can see the 0 and 0 for this is white, and one strip in the vertical, and the two strips, you can see the difference between this DCT image and the DFT basis images. So here you can clearly see the two stripes, and 1, 2, 3, and then 1, 2, 3, 4 black ones, and then here also this one here, and it would follow really in this. Similarly for horizontal, 1, 2, and then the 3, and then 4, and this is merged here. So 0 to 7. So if we have both, so you can see the 1 and 1, the black horizontal and vertical ones are becoming the diagonal one. So here you can see similarly this one and this pattern of cos, and which is different from the DCT. There you have the half cycle one, here it is full cycle because of that pi k by 2 n1, there it is 2 pi k1 n by n1. So the diagonal 2, you can see 1, 2, 3, 4 diagonal strips right here, and for 2 and 2. So similarly for 4 and 4, you will have this 4 and 4, you have 1, 2, 3, 4 diagonal strips. So it continues with the for the 7, and also you can see the property of it is after 4 n by 2. This is a repetition or the redundant information in the case of DFT. So you can see the same thing repeating here as well as here, and this would repeat at 8. So that's how it goes on. So the only n by 2 information is sufficient for taking the DFT. That's what we had seen that. So in this case, so up to 0 to 4 is sufficient. After 5, 6, 7 and 8 will be repeating 0. So it is not giving the extra information. So this can be seen in the basis images as well. And if we plot the same thing with the imaginary, so with the components which are used for this basis is sine 2 pi k1 n1 by n1, k2 n2 n2. So for k1 varying from 0 to 7, similarly, so you can see the imaginary one which has black and the white one, the interchange of it. 0 0 gives black, whereas in the previous case it gives you the white color. Okay, and one strip vertical and one strip horizontal, and similarly two strips vertical and two strips horizontal, 3 strips here and 3 strips as well, and 4 is this one. So you can have this scales repetition in this case. So 0 to n by 2 is the one which gives the information here as well. So this is for the imaginary part of the basis function. So you get this tile done. So the plot has been again with the tiled images of each one having the small axis, because this needs to be, this particular one is plotted with respect to this. Then what is the n1 and n2 for each basis images. So that's how we got this small patches of this, and these images are used in the to identify the what is in the image in the forward transform and in the inverse transform also, to get back the signal back. We use this basis images. So just to visualize this, how does this look like, and what is the correlation between the signal and this basis images, or the transform and basis images, so we get when we do the inverse transform. So the basis image, using that, how do we reconstruct, how do we get the transform? So once we have find the inverse DFT of this given 4 2 minus 2 0. So through an example we could see this as well. 4 2 minus 2 0, in which you can have the x, the coefficients are given, DFT coefficients are given. How do we get this x of n? That is inverse DFT, right? So if we use the IFT2 x of this, we would get the plot of images in terms of this basis images. So the real axis and the color map, we can have this as a gray. So the real of this x we get can be giving the color bar and axis of these images. You can see that it is 0 0, and then here it's 1 2 and 1. So this is the signal which was used to get this x of n. So you can see this black one and the 1 2 3. This is the basis image, 0 0 and 0 1 1 0 1 1 and so on. So we can from this, from the signal coefficients 4 2 minus 2 0, so we get a sequence which is, this is the basis image which can obtained from inverse f of t x. You can see that as well in the image form. That's it's easy to take the inverse f of t, the inverse DFT for the 2D signal. If we take that, and how do we, what is the information we get is the reconstructed sequence itself, 2D sequence. So that sequence we have just represented here as an image. So this is what the signal can be represented. So 1D, if you take the similar fashion of 1D DST, so DCT and the DFT we had seen what are the basis images. For the 1D DST pair, you know the equation of it, we had done the DST equation, and we have got the coefficients, and from that coefficients we have got the signal back. Also we had used the basis images to reconstruct it. So in this case, that x of n is the sequence, and it's a 1D sequence, and its basis function is sin pi k plus 1 to n plus 1 by n plus 1. So this is the factor which is used to here in the DCT. You need to have this. This is both in the case of transformed coefficients as well as getting back the inverse transform. Also we have the factor. So inverse DCT you have the 2 by n plus 1. So getting from sk, the x of n, we have this pi k plus 1 in n plus 1 by n plus 1. So in this example we'll see 4 3 minus 1 and 6. This is the sequence. Okay, so what is the DST? The coefficients. So the DST is that a discrete sine transform, as we have done in the previous lecture. So getting this DST is for a length of this, we had this DST coefficient, because this is having the factor square root of 2 by 2 n plus 1, and we fix this number of zeros first for 1 the row, and then k is varying from 0 to n minus 1 for the frequency components, number of frequency components we would like to check, and s equal to 0. And this summation, the equation which we had here is that this is summation of n is varying from 0 to n minus 1. So this case we have done it over here. S equal to s plus x of n plus 1 into sine by k plus 1 n plus 1 n by 1. So just implementing this equation, sine of that, and just summing it over with the previous values. That's the thing which we had done. So from this we can get the coefficients, and this s, and have this get multiplied square root of 2 by n plus 1, because it is used in the both the transforms, like forward and inverse transform. So this is x k plus 1 gives the coefficients of the DST. So DST coefficients can be displayed. That is one way of doing the obtaining the DST, so using the equation straightforward. So otherwise this we can do it with the alternate way also, so that in this directly using DST. So there is a command which can be used directly DST. So there are two ways always in this MATLAB. So you can do it from the scratch, which you know the basis function or the equation of the transform, the built-in function using the built-in function. Here is the built-in function DST. The same example with the DST x. So the coefficient here, it is not considering the factor 2 by n plus 1 square root. So we have multiplied it, and get the coefficients of this. So if you get the coefficients, those DST coefficients for both the cases of the examples 4.9205 and 0.2840, 5.27 and minus 3.1495. So these are the DST coefficients from which we can get back the sequence as well. Okay. Now getting the same thing for 2D DST, taking an x 2D sequence and obtained its basis images as well. Okay, so how the basis images are used in the reconstruction, we had proved it through an example analytically. So we'll give this same thing, we'll get it through the code. The x is 2342. This can be an image, a piece of image which can be of any values which has the intensity. It depends on this image matrix will have the intensity pixels, depends on the bit size of this image. 8-bit image, suppose 8-bit image, then that would have the pixels of 0 to 255. So here we have just randomly taken some values of 2342 just for an example, and this is the x for the image matrix. If it is just a simple 2 by 2 matrix, it can be of reality, it is not only simply 2 by 2 matrix, and the size is x comma 1, that is having this size, and fix the zeros for it to compute the DST coefficients, where k and n are varying. So you can have this equation of sine pi k plus 1 n plus 1 by n plus 1 and square root, just directly multiplying them. You can see the 2D case sk n plus 1. So this is having the sine, and once we have the case of sk, and how do we get the transformed one? Yes, x transpose, right? So that's the DST coefficient. F, or whatever the variable you want to use it, the alphabets can be used. F equal to s star s dash. So yes, here we have seen this in the example as well, is x transpose, which gives the DST coefficients. So calculating this s and then obtaining it for the 2D, x transpose would give the DST coefficients for 2D. So plotting them to create a 2D pattern of this basis images, this S and AS for column wise and row wise varying, or we can simply plot this for a particular basis image and then multiply with that coefficients also will do this. Color map, P and Q are taken for the particular row and column values here. So this is just to plot the values as an image. So the DST coefficients of 2D 5.5 and 0.5 minus 0.5 minus 1.5, we got it through this. So the corresponding basis images, we calculated the basis images also B of 0, 0. If you recall this example which we did in analytically, 0, 1 and then 1, 0 and then 1, 1. So these basis images has been used in the case of get this B here, which could give the details of the coefficients. So we can get back from this basis images its coefficient and its basis images are this. So once we have this basis images, we can use the transform the coefficient values and get back the sequence, 2D sequence as well. So for an example 2, suppose how do we get back this image? So to define this 2D DST and basis images for this particular image, which is having some values here, that it's shown with black and gray, and it's a gray image, it's not the RGB image, and reconstruct the original image from this 2D, from the 2D DST coefficients of it. So if we take the image, read the image, this image is a pixels.jpg which is generated, and imRead is the function to read the image and get the data, and check the size of it, and then convert if there is any RGB to gray X. So this one is the first thing that which needs to be done if you have an RGB image. So then at end, and if IM2 double, it will have the it will read those values of double X into in image double into X. After that, we can resize it for 8 by 8 or whatever the size you require it. Here this can be done for taking out the basis images. So take the size of this X, which decides this size m comma n, and then these matrices build the DST basis matrices for the 0. The important point is here is that S1, how do we get this sign of? So using the equation by kn m plus 1 for different S1 values to get it, and then similarly this is the DST equation, right? So the DST equation for the 2D, similarly for S2, S1 and S2 we got, this is for S2, sin pi kn by n plus 1. So once we have this kernel, using the equation that this is the kernel, right? So this one is the S1 and S2 are the kernels, and we can show this as a basis images. So how, using the tiled plot, that is using the tiled layout. So S1 and S2 shows the kernel matrices which we had generated. So plot it S1 S2 dash. So S1 S2 dash is nothing but the transform here. So we can plot it as a image section B and axis of. So the reconstruction is S1 X S2 dash. So S1 and S2 we got, that is the Y which is used in the 2D DST. So we can make it like S1 dash Y S2. This is transform. We can use it as well the other way also, because this having the properties of having this S1 dash and S2 dash also. We can use that property and we get the reconstructed image. So this is to show the image, and just want to plot the image which is having the 2D DST basis images. So here again the for this particular image we had taken the DST image, so we can get this using the basis images as we had seen in the DCT and the DFT. We can use this basis images as well, which is different from the DST image, is different from the DCT one. So the original image is this, and then we can use the DST coefficients. If you plot it, it's just giving that plot, and reconstructed image you can get it from that this coefficients what we have. So it looks like the block, it's not the block, there is a variation in this coefficients. So then we can get the reconstructed one. So just to show this images can be reconstructed using this how to get this DST from the image, and from this DST coefficient how to get this reconstruction. This is a forward and inverse transforms of that in terms of visualizing in terms of the images instead of the numbers of that 2D. In this lecture we have seen the basis functions of these 1D and 2D transforms, DCT, DFT, and in 1D as well as 2D, DCT, DFT and DST for both 1D and 2D. So we had visualize this through the images, and how do we implement this using the MATLAB code, and how do we generate and how do we get the coefficients for the given sequence, 2D sequence, and if we have the 2D sequence coefficients, then get the images or the original signal, 2D signal from that. So we will continue with the Hadamard transform and the other KL transform in the next lecture. Thank you.